So today our topic will be on first topic of today's class will be based upon transposition. So I'm going to write the definition of transposition first of all. Transposition is a topic from the chapter of permutation, and in the last class we discussed about permutation and permutation group. Also we discussed about symmetric group of order 3, and a few important theorems are also discussed. Now, to further proceed with permutation, we need to understand some other aspects of this particular chapter, one of which is called transposition. And in abstract algebra, definition plays a very vital role. So if the definition of a particular concept is not well understood, then we shall not be able to proceed with the problem. So let me write the definition of permutation first of all. Transposition. A permutation sigma on In, which is containing the first n natural numbers, is called a k cycle or cycle of length k if there exist distinct elements I1, I2, Ik in In such that when we operate sigma on I1, we get I2. Then if I operate sigma on I2, we get I3. Sigma of I3 gives you I4. And proceeding in this manner, if I apply sigma on Ik minus 1, we will get Ik. And lastly, sigma of Ik will give you I1. And not only this, sigma x will be x for all x belongs to some members of In other than I1, I2, ... Ik. This symbol which I have written over here is called difference symbol. Just like when we have two sets, capital A and capital B, A bar B or A slash B is called A difference B, and it means that if X belongs to A difference B, this implies X belongs to A, but X does not belong to B. So this is a recapitulation of this symbol, which I have used over here. So sigma X will be X for those X, for all X, which are in In, but not in this particular set. This particular set has been subtracted from the original one, that is In. So this is called the K cycle. Just look at the formula which is written over here. This is the form of the K cycle. So one I2 is obtained from its previous one, that is I1, then I2 gives you I3, then I3 gives you I4, and in this manner, you get Ik from Ik minus 1 and back to I1. So this is called the cycle. Okay. Now, what is the length of the cycle? How many elements that we have considered over here? We have considered small k number of elements. Therefore, this cycle will be of length k. And remember, this I1, I2, Ik, these are the elements which are distinct, and these are nothing but any of these elements present in In. So if you consider that small k is less than n, so you can consider some, say for example, n is 100. I can consider 50 elements, which are which when taken together forms a kind of cycle. This cycle can be can come in a haphazard manner, not in a sequential manner. Like if this 50 elements which forms a cycle has the first 50 natural numbers, say for example, out of first 100 natural numbers, it doesn't mean that this cycle definition doesn't mean that 1 will go to 2 and 2 will go to 3 and 3 will go to 4. Not in this manner. It's called a sequential manner. This cycle will be formed by these first 50 elements, but in a haphazard way. So for example, 1 goes to 50, then 50 goes to 2, then 2 goes to 25, and 25 goes to 33. In this manner, it will come back to 1. So that will be then, if these 50 elements out of 100 elements form a cycle, then the length of the cycle will be 50. So you have to be careful that these are not I1 plus I1 plus 1 doesn't give you I2. Okay, so you have to keep this in mind. But I1, I2, Ik be any of these elements 1, 2, 3 up to small n, provided k is less than n. Or it may so also happen that k is equal to n. That means that all the elements present in In actually forming a cycle. That can also happen. Now, if we consider a k cycle with length 2, such a cycle is called a transposition. Transposition. And transposition plays a very vital role in the study of permutation group. Okay, so let us try to understand this particular definition with the help of an example. We are considering a function, a permutation, which is given as this. And suppose it is written okay, and when we write this permutation, that means we have to be clear enough that we have to declare that this actually belongs to the group S6. The element of S6 which are of this form is based upon I6. We are choosing this 1, 2, 3, 4, 5, 6, this first 6 natural numbers from I6. And from there, we are actually constructing the elements of S6. Suppose you do not say that this permutation belongs to S6. You do not say anything like that. Then I can consider this permutation to be a member of S7 also. Suppose you will get to understand why am I saying so once we know the cycle. Okay, so this declaration that the permutation which I am considering belongs to the permutation group S6, this declaration, this context is very important. Now you carefully observe that under the permutation sigma, 1 goes to 3. And then under the permutation sigma, 3 goes to 2. Then sigma of 2 gives you 5. Then sigma of 5 gives you 1. And some other elements are present over there which have not been considered in this particular case, such as we have considered 1, 3, 2, 5. Now you see that in this particular permutation also, there are 2 other elements which are called 4 and 6, whose image is the element itself. So therefore, we are not talking about this particular elements over here, but we have ultimately got a kind of cycle. What sort of cycle we have got? Under the permutation sigma, suppose I am putting the element 1 over here, then I am putting the element 2 over here, and then 3 here, and then we have got 5 here. So we can express this thing diagrammatically as follows. So 1 is going to 3, 3 is going to 2, 2 is going to 5, and 5 is coming back to 1. So thus we have obtained a kind of cycle with respect to the permutation sigma corresponding to the permutation group S6. Now this cycle, how many elements are actually in I3? If I want to compare this particular example with the definition given above, now here the IN is actually your I6, which have first 6 natural numbers like 1, 2, 3, 4, 5, 6. And from this first 6 natural numbers, you are only considering 4 natural numbers. One natural number that you are considering is this one, 1. Another natural number that you are considering, 2. Another is that you are considering is 3. And the last one that you are considering is 5. So you can consider I1 to be your 1. You can consider I2 to be 3. Then you can consider I3 to be 2 and I4 to be 5. I'm just trying to correlating the definition, the expression given in this particular definition with the current example. Now see, these elements I1, I2, I3, I4 corresponding to my given example are any elements of I6, not coming in a sequential manner, because we know that after 1, 2 comes, but here according to the cycle, after 1, 3 is coming, then after 3, 2 is coming. That can happen in this kind of cycles. That's why I was telling that this consideration of these particular elements I1, I2, Ik may not be in a sequential way. Okay, so we have got how many elements you have got over here? 4 elements you have got over here. So actually we can form a 4 cycle from this permutation. We can form 4 cycle from this permutation. And how to write this 4 cycle? In a short form, we can write it in this manner. We can write it as 1, 3, because after 1, 3 comes, after 3, 2 comes, and then after 2, 5 comes. So we can write it as 1, 3, 2, 5. Now you are starting the count from 1. So you are getting after 1, you are getting 3. Then after 3, you are getting 2. And after 2, you are getting 5. Now one may start counting from, just look at the figure. One may start counting from 3 also. So this permutation 4 cycle can also be written as 3, 2, 5, and 1. Then some other people can also count, also can start counting from 2. So he will get 2, 5, 1, 3. And also you can start counting from 5. So you will get 5, 1, 3, 2. So all these examples which I have written over here, all these are valid because you can form a cycle starting from any one of these elements. The length of the cycle is 4. The length of the cycle is 4. But we know that if the length of the K cycle is 2, then it is called transposition. So my current example is not actually a transposition. It is actually, because its length is not 2, it's more than that. So this cycle has a length which is 4, but it is not a transposition. I hope that you have understood the definition of K cycle. Now, what I was talking about that when we say something about the permutation, and if there is a cycle present, we have to declare the context. Otherwise, we'll be in the trouble. How we are actually falling into the trouble without referring the context, that I'm going to explain right now. Let us consider my previous example. Let us take this cycle 1, 3, 2, 5. Now, suppose you are saying that we have a cycle. We have a cycle of length 4, which is 1, 3, 2, 5. You are saying just this, nothing else. No context is actually mentioned. Now, one can, and suppose in your mind, you are actually considering S6, but you have not declared this. Now, if you do so, if you do not declare, then what will happen? I can consider the permutation in the following manner also. 1, 2, 3, 4, 5, 6, 7. I'm seeing the rule over here. The cycle is showing us that 1 goes to 3, and 3 goes to 2, and 2 goes to 5, and 5 goes to 1. And 4 is going to 4 because nothing is mentioned about 4. 4 is not belonging to this particular set. 6 is going to 6, and 7 is going to 7. But you see, this permutation is actually member of S7. It is not a member of S6, but you wanted me to give the permutation of S6. That means we are not in an agreement. I am thinking about S7 and you are thinking about S6. So the result which you actually want to obtain from me, or the answer which you want to obtain from me, will not be correct one because of this misinterpretation. So to avoid the misinterpretation, whenever we talk about permutation or about cycle, it would be much better if we declare the context. So this context, as you already know from the mathematical logic section, the context is very important. Otherwise, the mathematics remains incomplete. And according to this particular example, now you can understand the symbol which I have written over here, that In minus I1, I2, I2. What does it mean? In our case, it is I6 minus 1, 3, 2, 5. And you know that I6 is a set and 1, 3, 2, 5 is a set. So this contains only two elements, which is 4 and 6. Okay. So that is the thing which is written in the definition. Now, let us try to discuss some another point. Because we already know the symmetric group S3 has already been studied. Symmetric group S3 has already been studied in the last class. We shall consider the group once again. Symmetric group S3. The elements of this symmetric group was, let us try to write these elements once again. First element that we considered was 1, 2, 3, 1, 2, 3. Then we considered another element which is 1, 2, 3, 2, 3, 1. We considered elements like 1, 2, 3, 3, 1, 2. Then 1, 2, 3, 1, 3, 2. 1, 2, 3, 2, 1, 3. And lastly, we have 1, 2, 3, 3, 2, 1. We shall now try to see whether we can express this elements of S3 as a cycle or not. Okay. Now, let us try to find this out. First of all, look at this particular element. That is the first one, 1, 2, 3, 1, 2, 3. Now we know that this is the identity element because S3 is a group and every group contains identity element. You have already known this fact that whenever we multiply any other member of S3 with this first member, that is 1 2 3 1 2 3, then the same element results in. So 1 2 3 1 2 3 is actually the identity element, and we are writing this as E. Go to the next one. Now you see, just look at this. 1 is going to 2. For the second element, 1 is going to 2. So after 1, I am writing 2. 2 is going to 3. So I'm writing 3. And then 3 is coming back to 1. So you see, I'm writing this element as 1 2 3. So it is a 3 cycle. Let us go to the next element. That means this one. 1 is going to 3 and 3 is going to 2. So I'm writing it as 1, which is going to 3, and 3 is going to 2, and 2 is coming back to 1. So the cycle here is also of length 3. It is called 1 3 2. Next, you go to this one. You see that 1 under the function of the permutation defined in S3, the one image of 1 is 1 itself in this particular element. But 2 goes to 3 and 3 goes to 2. So we can write it as the cycle 2 3. For this one, 3 remains 3. We can write the cycle as 1 2. For the last one, 2 remains 2. We can write the cycle as 1 3. Now you see that all the elements of the symmetric group S3 can be expressed as a cycle. This cycle is of length 3. This cycle is of length 3, but this cycles is of length 2. So in the symmetric group, actually we have found 3 transpositions. 3 transpositions are actually present in symmetric group. 3 transpositions in S3, because I already told you that any K cycle of length 2 is called a transposition. And here you see the last 3 elements of the symmetric group can be expressed in the following manner. And what about this E? What about this element? Is it a cycle? Yeah. Conventionally, we express E to be the cycle of length 1. Conventional, it is a convention that we consider this cycle as length 1. Sometimes in some authors express this cycle as just 1. Why? Because when we write just 1, it is a convention. You could have written just 2 or just 3. It means that all the elements are behaving in the similar fashion. That means 1 is going to, as many elements as are there, they are giving the same image, their own image under the given permutation. So it is a convention that we write it as just cycle 1. And since there is only one element, we call it a cycle of length 1. Identity permutation is a cycle of length 1. Just try to remember in the following manner. Now, here is another definition which goes like that. Two cycles I1, I2, IT, and J1, J2, JK of SN. SN means the symmetric group defined on IN, that is called SN, are said to be disjoint, if we consider the set I1, I2, ... IT, and if we take the intersection of this set with the set containing elements J1, J2, ... JK, this intersection will be phi. If such two permutations, if such two cycles you can find, then such a cycle is called a disjoint cycle. Now let us look at this cycle of length 3. Both of these cycles are of length 3. Say for example, I am considering 1, 2, 3, this cycle from S3, and 1 through 1, 3, 2, another cycle from S3. But you see, if you carefully look at this, if I consider the elements over here, the element of the cycles consist of the set 1, 2, 3 only for both of these cases. So therefore, the two cycles which are actually marked by green tick, these two cycles are actually not disjoint cycles. Disjoint cycles will be those cycles where the number of elements present in the two different sets with respect to the two different cycles will have no common element between them. Say for example, let us consider the symmetric group S6, and we are considering a cycle of the following form. Suppose sigma is 1, 2, 3, 4, 5, 6, and we are considering it as 1 goes to 3, 3 goes to 2, and 2 goes to 1, and 4 goes to 5, and 5 goes to 4, and 6 goes to 6. Suppose I am considering this. Now you carefully observe that we have got 3 different cycles from here. I am considering the cycle of length 3 and cycle of length 2. These two cycles I am considering. The cycle of length 3 here is 1, 3, 2, as you can see very well. And cycle of length 2 here is 4, 5. Now, corresponding to this cycle, the set is 1, 2, 3, and corresponding to that cycle, the set is 4, 5. And you see that intersection of these two sets gives you 5, because these two elements have no common member between them. Hence, 1, 3, 2 and 4, 5 are disjoint cycles. Now, there are some other important points, and an important theorem is there that I'm going to write. It's a very important theorem. Not only I'm going to write it, but I'm going to prove it also. The statement of the theorem says that let alpha and beta be any two disjoint cycles, in Sn. Okay, then the theorem says that alpha and beta will commute with each other with respect to the operation of composition. Here alpha multiplied by beta, it is not a multiplication operation, you know very well, because in the symmetric group Sn, the operation that we consider is the operation of composition of two mappings. Here alpha is a mapping, beta is a mapping, and we are considering their composition. That is denoted by alpha beta. Now, it is not always the case that alpha beta is equal to beta alpha. It doesn't happen always. There are examples, but just to save the time, I'm some topics that a few examples like this I'm keeping for you to study by yourself or look for in the book by yourself. I'm directly coming to the theorem. Remember that it is not always the case that the two compositions will always be a commutative composition, but there is a condition under which they become commutative. If you can find from the symmetric group two different cycles which are disjoint, and you know now what do we mean by disjointness, then the respective mappings with respect to the two permutations will commute with each other with respect to the composition. This result is very important, and I'm going to prove it now. So you just write it quickly because the time is also running out for the first session. Let alpha be the cycle which is defined as I1, I2, IT, and beta be the cycle which is defined as J1, J2, Jk. And suppose they are disjoint. Suppose they are disjoint. We will show that alpha, beta, their composition defined on the element X will be same as beta alpha defined on X. And this will be true for all X belongs to the set In containing n elements. Now, since alpha and beta are cycles, so you know that when we write that alpha and beta are disjoint cycles, then we can express them in the following manner. So according to alpha, with respect to alpha, I1 is going to I2, I2 is going to I3, and in this manner, IT minus 1 is going to IT, IT is going to I1. And not only this, Y goes to Y when Y does not belong to I1, I2, ... IT. This happens with respect to alpha. Now, similar thing will also happen to beta. Let us try to write it. Now, with respect to beta, J1 goes to J2, J2 goes to J3. In this manner, Jk minus 1 goes to Jk, Jk goes to J1, and Y goes to Y when Y does not belong to J1, J2, Jk. So, okay, I'm going to the next page. Now, suppose X is neither I1, I2, ... IT or J1, J2, ... Jk. Let us consider an element X which is neither of this. Then alpha X will be equal to X and beta X will be equal to X by the definition of alpha and beta. Hence, alpha beta of X will be equal to alpha of beta X, but you know that beta X is X, so we can write it as alpha X, and you also know that alpha X is X, so it is X. And similarly, beta alpha X will be equal to beta of alpha X. Alpha X is X, so we can write it as beta, and beta X is equal to X. So in both the cases, we find that alpha beta X and beta alpha X are same when X is neither of these elements. That is, neither it is from I1 to up to IT, or nor it is from J1 to up to Jk. Then it happens. Then alpha beta X and alpha beta alpha x are same. What will happen if they are not, these elements x is not like this? So suppose we are now taking the elements x, which is one of I1, I2, dot, 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 IT. If it is one of I1, I2, dot, 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 IT, then x will not belong to J1, J2, dot, 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 JK. Why is it so? Because it is already mentioned that the cycles are disjoint by the given condition. Since cycles are disjoint, it will not happen. Then since x will not belong to J1, J2, JK, so by definition of the permutation, beta x will be x, and alpha x is one of I1, I2, dot, 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 IK, IT. Hence, alpha beta of x will become alpha of beta x. Now, beta x is your x, so we can write it as alpha x, and beta alpha x will be equal to, or sorry, let me write it in this way. Beta alpha of x will be equal to beta of alpha x, and since beta x is equal to x for all x, and since alpha x is x, because of alpha x is one of these elements, so beta alpha x, since alpha x is one of these elements I1, I2, IT, so that means the element, as an element, alpha x is not also be belonging to the set J1, J2, JK. So beta alpha x will be equal to alpha x. Why? Since alpha x does not belong to J1, J2, dot, 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 JK. I don't think that I will be able to complete this proof in this session. So let's wait for the next session to begin.